Welcome, everyone. Thanks for joining the Iron Middle show today, the third episode, the Thanksgiving edition. As usual, we will be looking at Target Middle, how this particular distributed database works, why we code it the way it is, what's the underlying philosophy, and basically how to make a distributed database. So let's get started. Let me try not to repeat last two mistakes and actually start screen sharing. So yes, I see on the stream that my screen is shared. Hopefully you could also all hear me all right. So yeah, what's the topic today? Basically, I want to just walk through the path of a single message as it flows through a system. As a recap, what we have discussed so far is kind of like the overall idea about what target middle is. That it is a cluster, a distributed database, which talks with clients, which are the gateways through the networking protocol. So kind of like that's like the outer layer. Then we discussed what is the inner layer. That was the topic of the last episode. That inside we use where it is double entry bookkeeper. Yeah, double entry bookkeeper. Basically, that this is the whole data model of target. And today I kind of like want to connect those two together to go from bytes we receive on a network to actually processing transfers. Okay, do I want to say anything else in the intro? Oh yeah, and kind of like one. The most important thing is that like, well, why are we doing this? Well, we are doing this because last time someone asked the question like, why are we doing reference counted messages? Why aren't we doing like own messages? And I promised that it would take me 2 episodes to answer this question. And last time we learned part of the answer, which was that target middle batches transactions so that the overhead is amortized across a whole bunch of transactions. And that means that the reference counting isn't actually costly at all. And today we learn the second part of the answer, that, sorry, lost my train of thought. Yeah, we learned the second part of the answer, that we actually fundamentally need a reference count because message isn't actually owned by a single process. There is situations where like several concurrent processes work on the same underlying message. And maybe, just maybe today, we'll also touch this burning question of like, why are we looking at the zip code? Why are we like using Rust? But well, let's not put, I don't know, I need some Thanksgiving idiom, a turkey on the table before Thanksgiving. Let's do this in the proper order. And again, to walk through the path of the message, let's start from the beginning. Let's start from our main function. Okay, so here is main. This is what's run when you actually, I don't think we have run targetable even once, so let's try to, okay. I'm so far behind actually running the code that I don't even have a zip compiler in this folder. So, okay, we used scripts install zip to, actually let me bump. Let me bump the font here so that, okay. And I want 18. Yeah, much better. So yeah, I will use scripts install zig to install the compiler. Then zig build would actually build the thing, and now we like run this main code to see the target in action. It will take some time to compile, but we will patiently wait, just so that you see how to run a thing locally if you, for some reason, want to actually experiment with this. Okay, this puts target here, so we could run the format command, and this format is, yeah, right? The format over here corresponds to this format. And now then we can, okay, do I have start? Yeah, now we can start target all. Yeah, it will hopefully run the cluster for us. So yeah, that's the format, and that's the start. The code which actually gets the whole thing running, which assembles the graph of objects which point to each other. Okay, so there's kind of like a bunch of stuff there about static allocation, which we will discuss in some future sessions. Oh, this is actually like one fun bit. So we sometimes, well, in a lot of places in target we use random cryptographic numbers just as like nonces, IDs, or those sorts of things. And also sometimes we want to have like a special value which is invalid to distinguish a case where there is nonce from a case where there isn't one. And we conventionally use 0 to mean that something is not set. And that means that here kind of like we need to create a cryptographically random nonce which is non-zero. And like the question is like, how do you do it? Because kind of like this is like correct because the probability that you get like actual 0 if that's a cryptographically secure random number is like negligible, but also kind of like it could fail. So what we do here is we just say, okay, let's like do saturating add of 1 to make sure that that's not 0. But I'm actually wondering if we should probably perhaps just like, kill this, because if your cryptographic random number generator returns you a number which is 0, I think that's kind of like highly improbable, but not completely impossible. And if you get this behavior, that probably means like the most likely reason for that is that your cryptographic number generator is just broken. Like it's, I don't know, just some mix up in the kernel or whatever, so that it always like returns 0. So perhaps just generating randomly and then like asserting that it is non-zero would be more robust, just in case to protect from like some super messed up operating system, which doesn't give you real random numbers. Okay, anyway, that's kind of like step code. Then we create a replica. And I don't think we've seen replica yet, but replica basically is the main type in the taggable. Not in the sense that like it's like a vocabulary type and like there's a bunch of replicas and they communicate with each other. It's kind of like the basic stuff. No, the main type in the sense that this is the root of the object tree. So everything else which exists in taggable is a field of a replica or a field of a field of a replica or etc. etc. So basically kind of replica is the center of the universe. So what do we do with this replica? Okay, yeah, we open the replica. So we open the replica, passing it a bunch of options. Again, there's like a lot of code here. I'm going to skip all of this in this episode because I'm currently going to fully ignore consensus, going to fully ignore actual database access, and talk only about like messaging and execution of double-entry bookkeeping. So that's kind of like init method. A lot of stuff here happens, and finally we see something we've seen before. We create this message bus struct, and as a reminder, message bus is actually the network. It is called a message bus and not a network because this is where we decide to slice our system to create an abstraction boundary. So from a perspective of the rest of the system, the communication happens through messages. So replicas receive and send messages. Internally, this is implemented on top of TCP, but we kind of like don't really know that. Okay, so we create this message bus, pass it a whole bunch of stuff. But the core thing is that we pass it this callback function on message bus, which internally calls on message, which is a method on the replica, which like takes a replica. So self here is a replica. Oh dear, as it doesn't have */comments for a good reason actually. Okay, so we take a replica, we take a message, and we like dispatch it. Yeah, this is message bus. Then somehow this whole thing will be run. And if we come to the main and go back to start, we will see that after we open the replica, there's again a bunch of not really interesting login. There is like this tiny two-line event loop at the end, which just goes and like runs our event system. Okay, maybe we'll cover the details of message, like the underlying event loop, which is based on IO ring in this episode. But okay, for now, let's just ignore that and let's just say that there is like some kind of evented IO which runs the replica, and that evented IO gets plugged into message bus, which calls this callback when it actually receives a message. So okay, let's dive deeper. Let's dive deeper into this message bus, and yeah, here we hit one interesting aspect of Zig, that then you do go to definition for something which is a generic parameter. It's not really useful. Luckily, we name our files in like super straightforward way. So message bus lives in message bus.zip, so it's not too hard to find it manually. Okay, so message bus. That's like important thing. We actually have two message buses here. There is one in testing, which is like a fake message bus, which we'll be using for simulator. And well, yeah, at some point we will be covering simulator. But this one on the screen is actually the real message bus with the real TCP, because that's what we are interested in today, how the system works for it. Okay. So we allocate an array of connections, which is fixed in size. And this, again, touches something we will be discussing in the future episode, that like everything is statically allocated. And then we allocate connections again. Well, why? It's actually, why do we? Okay, so this is also connection. Oh, yeah. Okay, I think I got it. So these connections are actually like TCP connections to some remote hosts, which might not even be replicas. Like someone knocked us on our open port and sent us some like scene packet. We replied with an egg, and like someone's there, but we don't know who. So that's the connection. But after we actually communicate a little bit with that other end, and we figure out that, hey, that's actually a replica, we mark this connection as, hey, this connection is a connection to a replica, a member of our cluster, and not only just kind of like some random member, but a specific member. So in general, a cluster is like 6 replicas. And so this is a pointer. And like for the first replica, this will be null if we are not connected to the replica yet, or it will be a pointer to a connection from here if that is a replica, like if this is a connection to like the first replica or the second replica. And kind of the second, I don't mean that actually, yeah. Actually, let me explain. So when we start Tagbittle, you pass a bunch of addresses on the command line. Okay, so I'm pointing at the screen, but it's not really useful, so let me use my mouse. When you start Tagbittle, you pass an array of addresses, and this array should be the same across the whole cluster. The order of entries in this array is important, and kind of the first replica is like the first replica in this array. And because this array is consistent for the whole cluster, like the whole cluster understands the whole cluster is consistent with regards to who is the first replica, who is the second replica, etc., etc. Okay. So yeah, connections map from replicas to connections, and kind of like, well, I wouldn't say that this is a reason to use Rust over Zig. Well, Zig over Rust. But basically, kind of like this is already something which would be kind of a pretty nasty code in Rust, because here we have like a pointer from replicas to connections. So in Rust, you would like, well, you would use Rust syntax, and you would say something like replicas. I forgot how to use Rust. It would be slice, option, and view size, and kind of like that. That's going to be an index into connections. And again, that's not terrible. That's like pretty tame, but still kind of, yeah, it's extra indirection, extra stuff you need to deal with these direct pointers. Well, you could shoot yourself in the foot pretty badly here. But if you like don't, the actual code actually ends up simple. So it's kind of like a little bit bargaining with the devil here. But okay, again, as I said, we like only touch this today, but so I want you to do that. And like to clarify, this isn't actually like the reason like why we use Zig rather than Rust. It's not a problem. Anyway, let's go back to it. Okay, so we have our connections. And then we have our replicas, which are pointers to connections. We have our reference to I/O. So this is like that secret some ambient evented I/O, which is actually I/O uring, which we won't go into talk about today, but it is here. We can use it. Then there is kind of like a bunch of other stuff, and the core thing, on message callback. So remember, I said that when we create a message bus here, we pass this callback as a parameter. And here we can see this very same callback on message from bus on message callback. Okay. And yeah, one I can take that's the code which creates message bus. When things happen, well, things happen in this TCP method, where what we do, I think we should do two things here. We are a replica in a cluster. We want to talk to other folks in the cluster. That means that we need to create a TCP listener on one port. So we should be listening for incoming connections, but we also should try to connect to other folks. And I think initTCP is what's going to do this. Okay, so we open a socket, do some TCP stuff so that like it's actually like a useful socket and not like randomly slow thing. There's like should be like this. Let's disable, yeah, like let's disable TCP no delay. Like, okay, I'm not going to tell you about TCP no delay because, well, when I learned about it, I was just blindly debugging a super curious performance degradation in like my small TCP thing, and I like spent like two nights like figuring out what is it, and then I learned that it was like actually no delay. So it's kind of like very fun murder mystery, and I'm not going to spoil it for anyone. Yeah, and then we listen. But do we actually using IO here? Oh, yeah. So yeah, that initTCP doesn't actually. Oh, again, as a reminder, this is like unscripted, so I'm like reading code right now, and I don't like know everything. So when you see when I'm like fumbling around and like thinking like what the hell it is, well, it's because I don't really understand what it is, and I need to actually decode and understand. So I was thinking that TCP is the actual thing that like starts listening on the port, but that's not really the case. We just kind of like create a port, we open the port, but we don't try to accept things. But we've already seen maybe accept, and who drives this maybe accept? I have a hunch that this is a tick method. So let's find out who calls this maybe accept. Okay, yeah, that's a tick. And that's actually interesting, like another like big pattern in Target. If you go to main, you see that like in our event loop, we actually like do this like tick thing, which is basically, yeah, just every 15 milliseconds, we call this tick method, which is like basically the coarse grained timer. And inside this tick, inside Replica, yeah, we'll tick the message bus, and this would be this ticking method. And here, and here we're going to do two things. We try to accept a connection from pure Replica or our client, and we are going to try to connect to the different Replica. So let's look at the connecting path. So okay, we want to connect to specific Replica. If we have already connected to this Replica, well, we do nothing. So because we don't need to do this, and if I don't know if you, let's actually, well, we already this should be more easy. Oh, okay. So I was even just trying to connect to everyone here. So kind of like just what was, yeah. So just like for like 0 until bus request. It's actually not the case. So you have like n replicas and you want to create pairwise connections, but like you want only one connection. Like, and if like two replicas will try to connect to each other, they might end up with like two different TCP connections, which is not something that we want. So the rule is that nth replica only tries to connect to replicas with higher numbers. So that's why we start not from 0, but from the next replica. Okay, and yeah. When we migrated to music, we haven't migrated to modern for loop syntax. Okay, so we just try to connect to every replica which we should have a connection to. And if we don't have a connection, well, we don't need to do anything. Otherwise, we try to connect to replica. And this is, yeah, this like tries to use some kind of a timeout because we don't do, actually, how does this timeout work? Oh, right. So first we wait a bit, and then we actually like try to connect this. Wait, does it actually work? So I'm confused here because like we tick every like frame, and on every frame we are calling maybe connect replica. On every frame we are trying to connect if we have a free connection. And then we like try to do exponential backoff with jitter, but this. Okay, so yeah, basically what I'm saying is that okay, I'm super bad at like actually reading the code carefully and talking, so I will take a closer look after the stream. But it seems like we might actually do an exponential backoff here a little bit late. Like we should like every tick we like pick a connection and try to connect with replica, but only then we wait with exponential backup. So I would expect like here to have something like, I don't know, like basically there should be like if connection already backing off, like return. Maybe there is this logic somewhere, but okay, I'm not seeing it. Anyway, kind of, we could try to connect to everyone by using our IO to connect with a connect callback. And once we connected successfully, so here we have like the actual connection, we start scheduling, reading, and writing the messages. And okay, so let's trace the receiving part of the message. Actually, let me go back to the white triangle. So what I want to trace is like client request goes into replica. Then replica converts it into prepare, which is like needed for consensus protocol. Then it sends this prepare to other replicas who convert it to prepare OK, which sends again to replicas, actually like the primary. And then you actually got to meet the transactions. So right now we're looking at this this error here, getting a request from a client. Okay, so we look for path which reads a message. So we get ourselves a new message, kind of like an empty message, just a byte buffer. And then we say, okay, now let's make a receive syscall and schedule like reading into this message, because we message, okay, this should end in receive message. Yeah, and here we set this receive message. Okay, then we schedule the receive syscall, which says, hey, using like this file descriptor, like this socket from connection, or read some bytes from the network into this message, into this kind of like region in the message. And the connection internally tracks like how many bytes was received so far. Okay, so we schedule this or receive something later. The IO calls us back and says, hey, your IO request was completed. It either completed with error or it completed with certain amount of bytes. So, okay, if we are, in the meantime, if we can currently decided to close connection for whatever different reason, like, well, we kind of like don't process this receive. Otherwise, yeah, if this is actually an erroneous result, we try to receive a message, but we received an error and not like some amount of bytes. We can schedule a connection shutdown. If we receive 0 bytes, but also, well, that's look suspicious. That means that basically the other side, the peer, decided to gracefully close the connection, which is maybe unexpected, but anyway, we need to tear down this connection. Otherwise, we said, hey, kind of like we receive this amount of bytes. And again, there is no copy here, because the actual memcopy happens when we do this syscall over here. Okay, anyway, we receive some amount of bytes. We increased our cursor internally into this like in progress message, and we try to parse the message. This is the code which we've already seen in the first episode. So again, by this time you know the drill. For parsing messages in Tagbittle, we use like super stupid like bitcast protocol, where we just cast bytes we have received to header. We check headers checksum. When it is correct, we check when it is correct. That, well, when checksum for the header is correct, we know that the length, the size of the message in the header is also correct. So after that, we can just wait until we get enough data to read the whole message. And once it happens, we now can check that the whole message is correct. And again, as a reminder, we have like two checksums, because message starts with a small header and then a big body, like a header is like 200 bytes, and then the body is like a megabyte. We use checksum for the header to verify basically that this single size field is correct. And after that, we read the whole body, and then we checksum the body. Again, if we received something bad, that probably was a one-off error in like TCP, where like some byte got flipped. So maybe it would be correct to just continue using this connection and ignore just this single message. But again, like no harm done if we just restart connection, the whole connection again. So yeah, like, to be on the safe side, like reset the whole state here. Anyway, we if we receive a message and the checksum is correct, then, because again, TCP doesn't have framing internally, so in our buffer where we accumulate bytes so far, we might actually have been like, I don't know, like a message and a half. So we cannot use this message directly. We need to get a new message. And actually, I'm wondering, like, why are we even using a message here? Because it feels like we should just use maybe like just a byte buffer here, because we don't really like use message properties of this buffer, that there is like a reference count and whatnot. Again, something to think about later. So we receive the message, we copy this data, and this is like basically the single place where we do memory copy, and just to get rid of partial message. And return this message. Okay, so this was inside parse messages. Okay, so we get the message, and then we call connection on message. And this should do some handshaking, which we'll discuss at some time later. Well, no, actually, okay. Well, it's later. Anyway, so we get the message, and we invoke this on message call, which is, as a reminder, is this callback, which calls this callback. Sorry, like a lot of callbacks, and some of you might be wondering, like, where is async await here? And well, there is no async await here. There is like one good reason for that, one bad reason for that, and we'll cover again as usual later. I'm promising so much. I think like my platform in future will hate me, but well, that's his problem, not mine. Okay. We call a message, and finally, we can try to handle messages of different kinds. And so we kind of like, we want to look at the request. So let's look at the request. So only the primary processes requests. Why is that? Well, that we'll have to wait until we discuss consensus. But anyway, what primary does with request? The main thing which it does is converting this request into these prepare messages, which for now is again implementation detail of consensus, which we haven't covered. And yeah, so the way that the primary does this is by just like taking this message with all the bytes and just changing some fields in the header, specifically like this command field in the header, which describes what kind of message it is. So we kind of like just changing request into prepare is like very grand worded for what we say it is. Basically, it just primary just like tags this message as like, hey, this is a legit request for a client, and I, a primary in this view, like accept it with this op number. So probably, yeah, kind of like the two core things here is that we change the type to prepare, and we also assign the so-called op number. And this is the essence of like this single line is like the essence of like this whole like consensus and replication state machine linearizability distributed systems thing. Basically, that's like the whole purpose, that we have a bunch of requests which are submitted concurrently by the clients, and we want to order them in a single linear sequence. We want to assign like a number, an incremental number to all the requests so that we can process them in this specific order. We kind of like define, we create order. So that's kind of like simple line is actually kind of like pretty pretty important. And where do we increment the op? Okay, so here we say that the message op is like our current op plus 1, and here we assert that they are equal. So somewhere we should be, okay, there's a helpful comment here that on prepare is actually what handles this incrementer. So, okay, let's now see what happens when we convert this reply into prepare. Again, like a whole bunch of things happens. But the core is just these 2 lines. So let's actually like flow, like draw this flow. Client sends a request to sends request. Primary gets a request. Primary converts the request to prepare. Now, what we are looking at is that like primary processes prepare, but actually, as we will see, like not the primary, like every replica in the cluster processes prepare. Because the actual prepare processing is like these 2 methods, like replicate and append. Replicate means that we take this message and send it to other replicas in the cluster. And append means that we write this message to disk. And this is interesting. So you have a replica, you receive the prepare. This prepare is going to be part of the cluster state. So you should do 2 things. You should persist this prepare locally so that you can guarantee its durability. But you also want to tell your peers about this prepare because primary might not be connected to everyone. And like even if primary is connected to everyone, primary doesn't want to send prepare to all the replicas because that means that primary needs to have n times the bandwidth of everyone else, and that's bad because replicas are symmetric and their bandwidth is symmetric. So kind of like the work of distributing prepare across the cluster is shared across replicas. And well, actually, let's first look at the replicate because we don't want to get too far from a network right now as we are discussing the network. Okay. Oh, that's good. I've written recently, well, not so recently, but anyway, this is something I'm like super somewhat familiar with. Yeah, and the idea of replication actually that will require actually finally adding some new stuff here. So the idea for replication is that we do ring topology. It's like we don't want a primary to send prepare to every other replica because that needs too much bandwidth from a primary. So rather, we arrange replicas in a logical ring. And each replica in a ring sends the prepare to the next replica. So kind of like a replica receives the message and it relays it to one other replica. And that way, we share the bandwidth across the whole cluster. So, and kind of that's let's see how this connects to what we're actually doing here, like checking financial transactions. So what we do here, let's not number it just yet. Ring topology for replication, and we do ring topology for replication because bandwidth is limited. Like we want to, we cannot replicate from one node to everyone else because that might run out of the bandwidth on this like node which is primary. And this goes to mechanical sympathy, which is number 10, and also to efficiency. So let's say that this is like 20, and this is 21, which follows from 20. Okay. Now here there's actually kind of like two interlocked rings because we have like replicas, which are part of the cluster, and then standbys, which are part of the configuration, but we are not going to cover configuration, at least for quite some amount of time, so we could ignore this. And yeah, basically this is like the core idea. So we can like take our index, we add one, and we check if that replica is the primary. So the primary starts this chain, and once we get back to the primary, the chain breaks. But otherwise, we go and send message to this next replica, which contains a lot of assertions. Again, some of you might be wondering like why there is like so many assertions in this file. Like actually, how many assertions is in this file? Are there in this file? Sure, there's like 1,269. Nice number of assertions. Well, again, it's so many things yet to tell. So let's just now ignore all those assertions and look to the actual code, which would be send message to replica inside message bus. Which uses connection to send the message if we have this connection for a replica. Okay, what do we do with the message? Okay, we apparently have a queue of messages in a connection which tracks the messages we want to send. And kind of we drop we can place a drop a message if the queue is full, which again is like fine. Dropping messages inside our replica is fine because we don't assume reliability of the network, and we have all the necessary retries internally anyway. Okay. And then we start the process of sending, which issues the synthesis call using which message? Yeah, using like the head message from the queue. So we say, hey, let's send this chunk of bytes. And again, similar to how we have receive progress, which is a cursor. We have like send progress. So, and when the syscall returns, we attend progress, and if we send the message entirely, we drop this message. Yeah, we drop this message and start with like the new one. So kind of like that's how messages go inside and outside. So okay, that's kind of how. So what you've understood right now is that the client sends a request to a primary, then primary starts this daisy chain replication, which well, primary takes the request, converts it into prepare, and then starts like a daisy chain of replication until this prepare reaches every replica in the cluster. But in this on prepare, remember, I've said there are like two things. There's like replicate, and then there is append. Oh, actually, I guess there is an interesting thing here. Well, yeah. As you see here, kind of like the send method is kind of like fire and forget. So while inside message bus, we kind of like issue the send syscall, and we pass a callback, and the callback is invoked once a part of the message is sent to the network. On the replica layer of abstraction, okay, not here, yeah, here, we don't actually pass any callback here. So kind of like we just pass the message onto the message bus, ask the message bus, please kindly deliver this message to this replica, but we kind of don't actually care whether that message gets there or not. There is no callback here. Concurrently with that, because concurrently, like once we return from this replicate method call, we probably have made the send syscall, so the message is being sent by the kernel of the TCP socket, but the send is in progress. Like this is all on block IO. Concurrently with this, we do append, and the append is what writes message to disk. So, like we write prepare, and we call this like journal write prepare, and yeah, here we kind of like check whether we need to write a prepare. And I want to show you two important lines of code which actually explain why we fundamentally need reference counting. And yeah, okay, so let's highlight this one, and let's highlight this one. So what is happening here? On the left side, we schedule the message to be sent over the network. And on the left side, we schedule the message to be written to disk, to the write-ahead log portion of our data file. And both of these operations run concurrently, and they iterate on the exact same message, on the exact bytes of a message. And that's why we fundamentally require reference counting, because, well, we do two concurrent operations, they both access the same message. And we don't know which one of those operations finishes first. Okay, we have 8 minutes left, and let's just like quickly run through the rest of the algorithm. I think 8 minutes is plenty for that. Okay, so in Replica, in append, we call write prepare. In write prepare, we ask the journal, which manages disk. So this is like disk. We write prepare. Once prepare is written, we can guarantee its durability, and we guarantee durability by sending those prepare OK message from consensus protocol. And kind of like the high level idea or the consensus is that once enough replicas guarantee that they have written their prepare to disk, once we have a quorum of prepare OKs, it is safe to say that this prepare actually happened and accept all those transactions. So we kind of like, we send this prepare OK, and then on the other side, on the primary, we receive prepare OKs from replicas, and once we get a quorum, we say, okay, we can commit this prepare. So we go into the commit method, which is like complicated multi-stage thingy. because for committed, there are actually like many different paths how we might end up here. So the primary kind of like follows the edge. It like commits and prepares as they become committed in terms of prepare case. Backups listen to the primary and commit prepares as soon as we learn that prepare are committed. And then the third case is when a replica restarts and it needs to replay prepares from its log. So kind of, there's like a lot of different ways we can end up here. But for primary, we are going to be committing pipeline. And that's going to call this prefetch state machine, which calls this like state machine prefetch, which is a synchronous method. And then we do this like client replies, which is not super interesting. And then we finally do, yes, we finally do like the actual commit, which is like commit op. So this is like the actual commit operation. Okay. And somewhere here, we prepare a reply message. And yes, we call state machine commit method. Okay, and that is something we've looked at last time. A method which actually does this like double entry bookkeeping processing, which is how like everything connects together. So you see that there is kind of like a bunch of like flow from the client request to the state machine because of this like stupid consensus thing here, which is like hugely complicated. But basically here is that whatever bytes were sent to us by the client, they end up almost intact inside the state machine, which then processes it. But to actually get to this state machine, we have like pass through this like complex flow, prepare replica, processes prepares, append when done we send prepare org, then primary accumulates form of prepare case, and then like primary commits, which is again a lot of details. Very interesting details are missed right now, and we kind of like glossed through a lot of interesting aspects of the code today, which hopefully should give us kind of like food for thought for further episodes. So let's see how. Okay, let's maybe kind of like leave this as a cliffhanger. So what we have seen today? Well, first of all, we've seen a lot of concurrency. Inside message bus, kind of like we communicate with a bunch of replicas, we try to concurrently connect with everyone. We saw I/O loop, evented I/O callbacks. We haven't seen anything to wait. We also see concurrency between network and disk. Remember, kind of like this replicate append, which actually happen concurrently. Okay, this is kind of like super important. So let's go back here. So despite lack of a single rate, those are not working methods. What Replicate does, it's just kind of like fire and forget the prepare to be sent over the wire. And concurrently with this, we schedule the write of the message to the hard drive, which is okay. Which is not fire and forget, which we get notified about success through this write repair method, but kind of like still, that's like the core thing that this happens concurrently with everything else which happens inside Replica. Okay, what else? We've seen like lots and lots of assertions. And I guess, yeah, kind of like fixed number of connections, fixed number of everything else. Okay, so we are on time. The good thing about streaming is that I actually don't have to cut this exactly at an hour. Like I can go on and on, but I will probably try to wrap it here. So let's summarize today. We looked at the path that the message takes through the system, starting from starting a replica, receiving a message from the client, request from the client, converting it to prepare, OK, distributing it across the whole cluster using a ring topology, writing it to disk, accumulating a quorum of confirmations that the repair was successfully written to disk across the cluster, and then finally teaching our state machine to actually commit things, which is a lot, which is less than I would want to cover today. But well, I guess see you next week, where we will cover more of the stuff and kind of like try to add flash to this skeleton of processing which we discussed today. So probably, yeah, kind of like I'm annoyed that we didn't get to the actual meat of the things today, but also I'm excited that we like draw, like, it's like draw the rest of it all. We actually draw the outline. So now it is pretty clear what will follow next, but that is for the next week to find out. Thank you for tuning in. Thank you for watching or listening, and see you relatively soon.